In fact, any interactions between your system and the environment can be thought in terms of errors that are induced by the environment on your system, and those errors can be kind of digitized. So let's make a next step. Let's look at the more general scenario where we have a system, not necessarily a qubit, it could be a number of qubits, a quantum register, or whatever, relatively small compared to the environment that can have many degrees of freedom. So let's look at the situation where we have our system in state psi, an environment that has some fixed state at the very beginning. So we just assume that it's going to be in a pure state E. And then there is a unitary operation, the interactions between the system and the environment, that results in an entangled state of the system and the environment. So the claim is that you can always write this output state, the final state, as a sum over k, where k goes through all the basis states of the environment. So E sub k here is an orthonormal basis of the environment. And then there are some operators, we will call them quantum errors, not necessarily unitary. The only thing that we'll request from those operators will be the following condition, that the sum over k, ek dagger, ek is equal to the identity. So those operators act on the Hilbert state associated with the system. And they will modify the state of the qubit, and then there is a corresponding state of the environment, E sub k. Again, we saw that in the case of qubit, those operators could be the Pauli operators, but in general, they can be other operators. They don't have to be unitary. All that is required is this condition. So let's take a closer look how we can derive this final form. So first of all, we can write any unitary operator U in the basis of the system and the environment. So I pick up some orthonormal basis of my system and an orthonormal basis of the environment. So then in this basis I can always write a unitary on the composed system as a sum of I, J, K, L, U, I, K, J, L, where I and J will refer to orthonormal vectors from the system basis, and then K and L will index the basis, an orthonormal basis of the environment. So I can always write any unitary in this form, and then I can also rearrange this summation here and write this is a sum over K and L here, and let me just sum over I and J separately here. So I have U, I, K, L, J, I, J, and then tensor E, K, E, L. So if you look at this expression here, then you can see that this is some sort of operator that can be indexed by K and L, right? Because we sum over I and J. So that means that the whole expression for this unitary U is the sum over KL, E, KL, that is the operator acting on the system, tensor E, K, E, L. Now, as it happens in our scenario here, we fix the initial state of the environment. We assume that the initial state of the environment is just E. And we are interested in the unitary evolution under this condition. So if we fix E, we can choose E to be one of the orthonormal bases of from this set. So that means if we fix the initial state, then we can rewrite the whole expression here. So we're going to pick up EL. So say we just choose the first basis vector as the initial state of the environment. So our expression here can be then reduced to the sum over one index, so E sub k, because L is now fixed. Tensor EK, this initial state of the environment. So this is actually your unitary evolution, and then apply this unitary evolution to state psi tensor E, and then you'll get this expression here. Now this condition, though, is a direct consequence of the normalization. So if we want to make sure that the state after this unitary evolution is properly normalized, so we then require that what we have on the left, the input state, it's psi EE, so those are properly normalized vectors, and then they evolve into the output. We just have this state here, so the normalization condition is E K dagger E L K L, and here I have the scalar product of EK EL, right? So what I did, I'm just now calculating the scalar product of this state with itself, so the norm of the state vector at the output, and for this to be normalized, I want this expression here to be equal to 1. And so as you can see, that this is a Dirac's delta, right? KL, so that kills one index. So effectively we require then psi sum over k ek dagger ek psi is equal to 1, and that is for all possible states psi. So we can vary those states. Remember, the state of the system could be just anything, but we fix the state of the environment in this scenario. So this expression here, we require the normalization for all possible input states psi. So that can only be satisfied when this expression here is equal to the identity, because we assume that the initial state is properly normalized. So here we have a situation where we start with the initial state of the system in some, say, state psi. We fix the state of the environment. We have a unitary operation, and the resulting state, the output state, is the state which can be written in this convenient form. You can think about E sub k as quantum errors. Now, one thing that you may sort of wonder here is that, well, you know, the environment is huge, right? So so there are many vectors E sub k here. So that means there will be just like a huge expression, so that the summation over k can go from 1 to a huge number, which may not be something practical, but as I'll show you in a moment, that's not necessarily the case. You can actually truncate this, because what really matters in this particular case is the dimension of the system, and then we can decompose any of those quantum arrows, those operators, which are matrices d by d, where d is the dimension of the Hilbert space associated with your system, we can just pick up a convenient basis for the operators acting on this Hilbert space, and there will be no more than d squared of them. And this will come in a moment. But the message now is that you can always think about system-environment interaction as something that results in environment inducing some errors on the system. And of course, in this particular scenario, you can really say that error E sub k happens, and because we assume that the states of the environment are mutually orthogonal, so they form an orthonormal basis.